Welcome. Today is the fifth lecture in the series, and the last four lectures we have already given a brief introduction to marine hydrodynamics, flow descriptions, equation of continuity, which physically mean the conservation of mass, and we have worked out several examples. Now, today lecture will concentrate on equation of motion, and basically will whose physical significance is law of conservation of momentum. And when we think of law of conservation of momentum, we always Newton's second law of motion comes into our mind, because that says that rate of change of linear momentum is equal to the total force that is acting on the fluid. In today's lecture, while discussing in the equation of motion, we will assume that it is for non-viscous fluid, that is inviscid fluid, and hence the equation we will concentrate today on Euler equation of motion. What we call this is the Euler equation of motion. So, when we think of law of conservation of this equation of motion, particularly the force comes into picture, and when you look at forces acting on a fluid element, always look into what are the forces. Let us look into what are the forces acting on a fluid element. When you look at this, there will be two types of forces which are acting. One is the internal force, and the other one is the external force. The internal force always they balance each other, and their sum is 0, as every action has equal and opposite reaction. On the other hand, when we think of external forces, there are two types of external forces. That is always one is called the body force, or rather we will say surface force. External forces are surface forces, and the other one what we call the body force. The surface force always act on the boundary of the particle of the fluid. On the other hand, body force is external force, and this body force, that is always like forces like gravity, basically gravitational force of attraction. If the body is in a magnetic field, then magnetic force, gravity force, magnetic force, and also other applied forces are capillary forces that acts on the capillary forces, that is due to surface tension. Then we have geostrophic forces. And that is this is caused due to the Coriolis acceleration due to the rotation of the earth. Now, with this, so these are the various forces which act on a fluid element, and then another thing is what we say, that is conservation of a vector field. What I mean by conservation of a vector field? Suppose let us consider two elements. Let F be a vector field, let F be a uniform vector field within a region R. And let A be a point here and B is another point here. So, what will happen? What is the integral A to B F bar dot dr bar? If this is same as A to B F bar dot ds, and this from this to this, the integral it can be, we can think of in many direction. So, here what we have taken dr bar is ds. So, if the value of the integral, this value of the integral from A to B is independent of path of the integration, whether we go from this way, whether we go from this way, whether we go from this way, whether we go from, if it is independent of path, then we say the value of F in R said to constitute a conservative vector field. So, that is the way we define a conservative field. Now, there is a, let us see what is the necessary condition, necessary and sufficient condition for a vector field to be conservative. For a conservative vector field, the condition is that, as we have said, that if F is a uniform vector function, this is result, F is a function in a conservative vector field in a region R, then the field F is said to be conservative in R if there exists, if we can find a scalar function, there exists a scalar function phi such that we can represent grad of F bar equal to grad of phi. If this can be done, then we call this as a, this vector field as a conservative vector field. One of the best example of a conservative vector field is the gravitational field. If I take F bar is 0 g 0 basically in the gravitational field, so I can always find, if I look at the function phi as a g y, g the gravitational force, and if phi is g y, then automatically I will get grad of phi is F bar 0 g 0. So, because of this, we always say the gravitational field is a conservative field. Now, before going to derive the equation of motion, I have another result to tell you what is the Gauss theorem. This is the theorem which is, it can be easily obtained from the, this theorem can be obtained from the Stokes, this divergence theorem, that is, and this theorem says tau grad of A d tau is equal to integral over S A n hat ds, where what is S? Let us look at a surface, yes, and let the total volume in enclosed to the surface is tau. Then if I have element ds, if I have an element ds, then draw, there is a normal you draw here n hat unit normal. Then we have tau is the volume, so grad A is any function, scalar function A is a scalar function, so then grad A integral over tau d tau is integral over s a n hat ds, and this is a very important result which we will be using in the derivation of the Euler equation. Now, as I have already mentioned, then let us come to the Newton's second law. Of motion, because this is basically based on this. So, this says, as I have already mentioned, this is the rate of change of linear momentum with respect to time is equal to the total force acting on the fluid mass of arbitrary volume fixed in space. So, this and our law of conservation of momentum, which is this is the law of, often we call this as law of conservation of momentum. Now, to derive the equation of motion, what we will do, let us consider again, suppose we have this tau is the total volume and s is the surface, then ds is an element. Let d tau be an elementary volume. Within the fluid mass. Bounded by the surface bounded by ds, and as usual I will say rho is the density of the fluid, density, and let if q bar is the velocity, if let us say q bar be the velocity vector, then the rate of change, then the momentum for the elementary mass m, momentum over the elementary volume d tau will be rho d tau into q bar. So, hence the rate of change of momentum for the elementary volume d tau, which will be d by dt rho q bar d tau. Then if I have my total volume is tau. So, if total volume is tau, the total, so the total for total volume tau rate of change of momentum this will be integral over tau d by this, I can call it, this I can take it as d by dt, because I am rho is a function of x y z t. So, always, So d by dt rho q bar d term. Now let F be the force, let F bar be the force, that is the body force, because we have two forces acting on the fluid element, one is the body force, one is the surface force. F bar be the body force per unit mass. Acting on the elementary volume data. Hence, we have the total body force acting on tau will be integral over tau rho, because rho F bar rho d tau, because F bar is the body force acting per unit mass, so rho is the density, so and tau is the total volume, so rho F bar d tau integral over tau, and this integral is a volume integral, that is the total body force acting on tau. This is the volume, total volume. Now let us look at the surface force. Let P be the surface force per unit area. Hence, if you look at that, what will be the total surface force? The total surface force will be, we have P n hat ds, that is on each small element ds, and our total surface is s. So this will be P n hat ds. This is the in the outward direction, but the hence the total external force, as we have seen that the total force acting is the one is the body force, one is the surface force. Hence the total external force will be a combination of the body force and the surface force. So that is integral over tau P n hat ds, and this will be a negative sign because the forces, this n hat is in the outward direction and this force is acting in the outward, but our where force is acting on the fluid, so there will be a negative sign plus the total body force rho F bar d tau. Now we apply the Gauss theorem, that will give us integral over tau, that will be give us rho F bar minus gradient of P d tau. We have used the Gauss theorem as I have already mentioned. Now this is the total external force. Now if I go back to the law of conservation of momentum, as I mentioned that this is should be equal to the rate of change of linear momentum, and if I do that, the rate of change of linear momentum, then that will give me integral over tau d by dt rho q bar d tau, which is equal to integral over tau rho F bar minus gradient of P d tau, which gives me integral over tau d by dt rho q bar plus rho F bar minus grad of P d tau equal to 0. Now since tau is arbitrary or tau is arbitrary, so we can always say if I say tau is d tau, if tau is d tau, then what will happen, which implies d by dt rho q bar is equal to plus rho f bar minus gradient of p equal to 0 for if tau is d tau is not equal to 0, then we have this, and this is what I say, this is called the Euler equation of motion, Euler's equation of motion. So if rho is constant, if I say rho is constant, then this gives me d by dt q bar plus 1 by rho, this is minus or this is minus, so this will be, or this will be right side, or this one, sorry, there will be a minus sign here and this will be plus 1 by rho grad p minus f bar equal to 0. So this becomes, if rho is constant, then this becomes this, and in this I can always, this also I can always write del q by del t plus q bar dot del into q bar plus 1 by rho grad p minus f bar is equal to 0. So this is the inertia term, this we call the inertia term, sorry, this is the inertia term, these are the two terms of the inertia terms, this is the surface force, rather I will say that these two terms, they are the body forces. So inertia terms, inertia forces, rather I call it inertia. So this is the inertia force and these are the body forces, and this I can call this as local inertia, and this is the convective inertia term, this is called the surface force, and this is the external force, applied force, particularly this is the body force, this is the body force, this is the surface force. So body force is this term, and this term I call this as the surface force, and then this is the local inertia, this is the convective inertia. In other words, I can always say this, I'll just write it for sake of clarity. This is del q bar del t plus q bar dot del bar into q bar equal to f bar minus 1 by rho grad p, and here in this equation, so we have one is the local inertia, this is the local inertia force, and that is, and this is the convective inertia, convective force, and this is the net, I call it net body force, and this is your surface force. Now if I take f bar, because in a gravitational field I can always take f bar is 0 minus g 0, and if I assume my q bar is equal to UVW. Then in the Cartesian coordinate system, this Euler equation should be reduced to del U by del T plus U del U by del X plus V del U by del Y plus W del U by del Z minus 1 by rho del P by del X, and del V by del T is at the Y component plus U del V by del X V del V by del Y plus W del V by del Z minus 1 by rho del P by del Y minus G, and then we have del W by del T plus U del W by del X plus V del W by del Y plus W del W by del Z. This is what minus 1 I rho del P by del Z. So this is these three equations are the equation of motion in the Cartesian coordinate. Now, in the derivation of this, we have neglected the viscosity. We have not taken into account the effect of viscosity. Viscosity is neglected, and we have considered the fluid as incompressible because we have taken rho as constant. In this, so these two important assumptions we have made. But what will happen? And also, we have not taken into account the surface tension effect. In addition, the thermal conductivity of the fluid is also not taken into account. So this is one of the very ideal situation, and we sometimes call this as the ideal flow. If the Euler equation is satisfied for any ideal fluid. Now with this, if I just say that my flow is potential type, if flow is a potential type, I will have Q bar is equal to grad phi. Q bar is grad phi, and I have curl of Q bar is 0. And further, since I am the gravitational field, as I have mentioned, that I can write F bar is grad of minus Gy. Further, I have another relation that Q bar dot del bar into Q bar. I can always write it in the form half of del of Q square with the minus Q bar cross del cross Q bar. Since my flow is rotational, I have already taken curl of Q bar is 0, so I can and again I can always write, since my flow is homogeneous, assuming the flow is homogeneous, I can always write grad P by rho as grad of P by rho. Under these assumptions, I always can write from my equation of continuity, Euler equation of motion, del Q by del T plus Q bar dot del bar Q bar is F bar minus grad P by rho, which I take a small p, which I can write in this form grad of, because I substitute for, I will write it as del phi by del T. So Q is grad phi, so grad of del phi by del T, then plus this also, because I am taking this part is 0, so q dot del q bar is, I can write it grad already taken, then half of, I can call it as q square by 2, and then I have also taken which is equal to grad of minus gy minus grad of, I can take in the bracket, so p by rho I can take it. So which implies I can also tell this as del phi by del t plus q square by 2 plus p by rho plus gy grad of this equal to 0. Now if I, from this I can always if I take the gradient, if I take the dot product with dr and integrate it, from this I can always get del phi by del t plus q square by 2 plus p by rho plus gy is equal to, because I am gradient, I am taking the space derivative, so it can be a function of t, and this function can be arbitrary function. So this is what I call this equation as the Bernoulli equation of motion. Equation of motion for irrotational flow. So this f is arbitrary. Now this Bernoulli equation plays very important role, in fact in many problems of hydrodynamics, particularly in the marine environment. When we calculate the wave forces on a structure, we always take this Bernoulli equation into account to calculate to know the hydrodynamic pressure, and from there we integrate it over the surface area to get the force acting on a fluid element or acting on the body. In fact, again, when we have a free surface in the water, we have a free surface, and in that situation also we use the Bernoulli equation to calculate the, because you have a atmospheric pressure here, P atmosphere, this side is P, H is the hydrodynamic pressure. What we do at the free surface, we equate the atmospheric pressure with the hydrodynamic pressure, and to get the dynamic free surface condition. On the other hand, in the last lecture I was talking about the surface boundary condition. I was talking about the surface boundary condition, and there we have seen if y is equal to eta, if y is equal to eta xt is the free surface boundary, then we can always say that d by dt y minus eta xt equal to 0, and that gives me the boundary condition, another boundary condition, that is the surface boundary condition. So on this water surface of a fluid, we have two conditions. One is the surface boundary condition, we call this as the kinematic condition on the free surface, and this one, that is when we relate the atmospheric pressure with the hydrodynamic pressure on the free surface, because on the free surface atmospheric pressure is same as the hydrodynamic pressure on the free surface, and that gives us dynamic free surface condition. So this is one boundary, y is equal to eta, where two conditions are satisfied. One is the kinematic condition and one is the dynamic condition. So this equation of this Bernoulli equation is very crucial, even if in coastal engineering applications, when we consider the flow is rotational and inviscid, to calculate the forces on a breakwater and calculate the surface elevation and other physical quantities, this potential flow analysis will always apply, and for the force calculation always use this Bernoulli equation. Hence, and also in offshore structure, wave load on offshore structure, even if on ship and any other marine structure, we use this Bernoulli's equation frequently. Now, if I in the Euler equation, if I assume that the flow is steady, if motion is steady, then that time derivative will go. We will have del q by del t will be 0. Once del q bar by del t is 0, then the Euler equation will reduce to q bar dot del into q bar is equal to f minus grad p by rho. And again, if we say that the flow field is conservative, and we can write this is a fluid is homogeneous, then we can also write grad p by rho is grad of p by rho, and if f bar, you can also write it as grad of gy, assuming the field is a vector field. This vector field, the gravitational field, is a conservative field, and here conservative field is the gravitational field. And again, so we can always write, and again we utilize the same relation that q bar dot del into q bar equals to half of del q square minus q bar cross del bar cross q bar. Then we can always rewrite the Euler equation of motion in case of steady flow as q bar cross del bar cross q bar as del of q square by 2 plus this is minus gy minus gy minus gy this will be f minus, or q is here, so this is f is minus, so once you put this will be q square by 2 plus gy plus p by rho. Once we have this is a plus sign. Now there are two cases, few cases comes in. Now if q bar cross, this is nothing but curl of q bar. If this is 0, case 1 curls like this, that means the streamlines and vertex lines are parallel. In this case, your streamlines and vertex lines are parallel, or they coincide, If they coincide, for such motion q bar is called a Beltrami vector. So under this, when the streamlines and vertex lines are parallel or coincide, q bar is called a Beltrami vector. In that case, the left side can be 0. Another case comes when curl of q bar is 0. That means if curl of q bar is 0, that means flow is rotational. In both the cases, this gives us d of q square by 2 plus omega plus p by rho is equal to 0, and which can give us del of this is 0. Which gives us, if you integrate it, you can easily get it q square by 2 plus omega plus p by rho is 0, and here this omega is nothing but gy. So this is, so whether the flow is rotational or irrotational, this equation will be satisfied. Another case comes case 2. Suppose you have q bar plus del cross q bar is not equal to 0. If this is not equal to 0, that means if this is not equal to 0, this vector q bar cross del cross q bar, these two vectors, this vector is perpendicular, they are perpendicular to q bar as well as del cross q bar, they are perpendicular to this and this. Then, and if dr bar is not equal to 0, this is the tangent, then dr bar, yeah, this is the tangent and they are the perpendicular, they are perpendicular to this. So I can take dr bar dot q bar cross del cross q bar is equal to 0. And once this is 0, so from the right side I can always get d of, because that is also del, and when I say q dot dr bar dot del of this, that will give me d of q square by 2 plus omega plus p by rho, that is 0, and this gives me q square by 2 plus omega itself is gy plus p by rho, that is equal to a constant. In this case, because unlike the other case, in this case the motion is steady, so this constant is independent of time. So what does this gives me? This gives me that the combination of 3, so I have q square by 2 plus omega is gy plus p by rho, that is equal to constant. And this motion, this is independent of time, and this is often, I call this as the velocity head. This is the velocity head, this is the gravitational head, because the gravitational head, and this is the pressure head. So that means the velocity head plus gravitational head plus pressure head is constant when the fluid is steady, and in this case we have assumed the flow is along a streamline, because we have taken dr is not equal to 0 and flow is steady. Fluid is also assumed to be incompressible and homogeneous. So this, I will just summarize this. When the flow is along a streamline, it's a streamline, and then the flow is steady, and the fluid is incompressible, or homogeneous, and here we have already said it is inviscid, non-viscous. So then in that situation we have the pressure head, velocity head plus gravitational head plus pressure head is constant. And here another thing, here it comes to mind that in this derivation, either the flow is this is suitable for either the flow, whether it is a rotational, this also holds good for both rotational as well as irrotational flow. So in both the cases this will hold good. So what we have done today, and in this case we have steady motion. When we have unsteady motion, we have seen the Bernoulli's equation, and that is for unsteady motion, and this is what I say the Euler equation for the steady motion, or sometimes we also call this as the Bernoulli's equation. In this case, one of the thing is that it is here the fluid can be rotational, or rotational. And in many pipe flows, to calculate the pressure, always these equations are taken. Particularly in hydraulic applications, flow in a pipe, or various application in civil engineering, this equation is taken into account. On the other hand, when it comes to marine hydrodynamics, particularly ocean engineering, we always emphasize that the motion is always, we don't assume the for unsteady motion, basically we always deal with, and in that situation we apply the, although of course here we assume that the flow is irrotational, and in that case we apply the Bernoulli's equation, that is your del phi by del t plus half of q square. There we apply that equation, del phi by del t plus half of q square plus gy plus p by rho is equal to constant, or f of t. This is another form. So, and in this case q can also, we can write it as q as the component u, that is phi x phi y. So we can write in terms of phi also, this term we can also write in terms of the velocity potential phi. So we have already, now today we have already derived the two things, Euler equation of motion and then the Bernoulli's equation, and these two equations of motion is somehow different, because in both the cases we have assumed that viscosity of the fluid viscosity is negligible, and when we will take the fluid viscosity into account, the corresponding equation will call them, the corresponding equation of motion will call this as the Navier-Stokes equation, and we'll come to that much later, and we'll work out few problems, particularly how to calculate the pressure and force when the flow is envisaged, how to calculate the force and pressure. Once we know the pressure, we can easily calculate the force. So this is a very simple way for envisaged flow. We can easily calculate the pressure on a surface, and once we know the pressure, we can calculate the force at each and every point, or on the body, that is. And as I have already mentioned, in ocean engineering, this equation will play a very big role, because wave load calculation plays a very important role in the design of the marine structures. Basically, whether we have today, we are concentrating more on various types of offshore structures, because the various aspect of flow and in ocean, major analysis we do, particularly when we calculate the wave load on large offshore structures, large floating bodies, or even upon coastal structures, then we always assume the flow is incompressible, fluid is incompressible, flow is rotational. However, the complexity there we always face, because we have two, as I have mentioned, that we always come across two conditions on the surface, and both the conditions are highly nonlinear. And here, in fact, the surface is very dynamic. Although we will deal with a potential flow problem, we will be assuming that the flow is potential type, rotational motion, so flow is potential type, but still the complexity of the problem remains, because on the free surface we have two conditions, one is the kinematic condition, one is the dynamic condition, and this dynamic and kinematic condition, when you couple them together, that becomes more complex, and that brings a lot of complexity. And this kind of problem particularly occur in marine hydrodynamics. Even if the flow is potential kind, the problem complexity remains because of the nonlinearity free surface, and this is how the other problems, this is differ. There is a significant difference about this branch of hydrodynamics than the other related branches of fluid mechanics, where free surface does not play much role. Look at a pipe flow. Even if you consider the viscosity, the complexity of the problem is simpler problems are much easier. Some of the problems are much easier, whereas in this case problems are complex. It is because of the free surface condition where we have nonlinearity occurs, although we solve a Laplace equation. I will come to in detail to those water wave problems in few of my lectures, but before I have few more things to complete in this, because I have to calculate. So, how to calculate the pressure when a body is moving. We have already been aware of few problems. We will work out few more problems and try to understand how we are calculating the pressure on a structure, or when a body is in a fluid, how we are calculating the force acting on it. And with this, today's lecture I will conclude, and next lecture will again come back to two-dimensional flow, and there will emphasize some more problems where the how to calculate the pressure and force, and then we will go to analyze some of the aspect of the problem like source, sink, and after that we will come back to, after source sink we will come back to hydrofoil and aerofoil section, wing aerofoil theory, and there also will come across this calculation of the force, that is how the forces are acting, how the force and movement are acting. In fact, in many situations we will see that this envisaged characteristics will play a significant role, and in practice it gives a very good result, although in many situations we assume that the fluid is a non-viscous, but it gives very good results in many cases. Anyway, slowly we will go into the details, and today we will conclude this today's lecture here. Thank you.